There's a lot of talk about achieving a fifth-generation wireless network by 2020, but there's still a lot of work to do on the 4G wireless technologies. Long before we get to 5G, here in the TI Now studio to give us a glimpse into the path to 5G are four panelists. To my left is Eric McLaughlin. He's Director of Product Management at DragonWave. Next to him is Farouk Khan. He's President of Research at Samsung's Lab. And next to him is Glenn Hunt. He's a Senior Analyst at Current Analysis. And last but not least, Joe Sandry, Senior Vice President at Fiber Tower. Gentlemen, welcome to the program.
Thank you.
Yeah,
Thanks for being here. A lot of things happening down on the floor. Of course, we're here at CTIA 2014. We appreciate everyone coming up here to our suite and having and spending some time with us to talk about this path to 5G. Farouk, I'm going to start with you. I want to ask you a very challenging question, if you will. If you can, and I know there's not a definition per se for 5G, but give us your definition of 5G and let us know, is it just speculation now about the capabilities for 5G?
Okay. So our vision for 5G is gigabits per second for every being and for everything. Currently, 2/3 of the humankind does not have access to the internet, wired or wireless. 3G and 4G was all about providing access to information for the select few who can afford it. 5G will be different in two ways. First, it's going to make access to the information ubiquitous and affordable for all humankind. Secondly, it will provide capabilities for universal capture of information via myriad of sensors and devices in Internet of Things. And coming back to your second point, we know that every new generation of mobile communications happen every 10 years, starting with first G in the 1980s, 2G in the 1990s, 3G in 2000, and 5G deployments started in 2010. With this trend, we can expect 5G will be deployed starting in 2020. We have already done the feasibility study and channel measurements of 5G, and now is the right time to talk about 5G requirements and standardization.
Eric, a big part of this path to 5G, if you will, is the adoption of small cell technologies. What is one of the, barriers to that adoption?
Yeah, so with 4G networks, you're seeing a densification of the network. So you're starting to see cell sites that are being deployed in, I'd call them non-traditional infrastructure. So sites that are being deployed on lamp poles, traffic lights, side of buildings. So what this does, this represents a challenge on the backhaul, right? Because you don't typically have wired infrastructure. Fiber doesn't go to most lamp poles. Fiber doesn't go to traffic lights. So backhaul is a critical issue with that. So one way to address that is wireless backhaul, right? So with wireless backhaul, you need to start considering, because now you have to add an additional element to your overall solution. So considerations on power, space are critical issues, as well as spectrum availability for the backhaul is also important.
Mm-hmm. And just to, in addition to the backhaul is definitely the number one challenge, but also the cost, both for the front end and the site acquisition cost, as well as the making the form factor suitable for these new deployments.
Glenn, we just talked about a couple of the challenges for this, quote unquote, path to 5G. But one of the technologies that might get us there is millimeter wave technologies. Can you give us some of the primary tenets of millimeter wave technologies?
Right. Well, I think it goes back to a point made earlier about available spectrum. There's a need to have more spectrum available, and that's certainly a good way to get there is to start to talk about using the spectrum in the millimeter wave area. So really kind of two segments there that in my mind there's the 60 gigahertz spectrum as well as the 80 to 90, or the E-band versus the V-band. What we're seeing there is the option to actually increase bandwidth on those microwave links by using that technology. The 60 gigahertz makes a lot of sense for small cells because it's short distance, high capacity. The E-band makes more sense for longer runs, higher capacity as well. So that's really kind of the stepping stone that we see moving forward. The other issue I think that I see is with the cost of the infrastructure, as Farouk pointed out, because you have many cells. and you're trying to get to about 1,000x the bandwidth total aggregate capacity. That's an extremely high cost given today's technology. So I think we're going to see increasing pressure on the devices that deliver that capacity to be much more efficient, get a lot more out of the spectrum that's there today. And even though we're talking about future spectrums, even beyond the V and the G band, there's a number of studies that have been kicked off by major universities, NYC Poly, for example, and there's also a European Union-sponsored study where we're talking about opening up many, many more spectrum segments that even go up to, I think, as high as 275 gigahertz in the future. So by the time we get to 2020, there's a lot of these steps that have to come together in order to get the capacity at the price points that we're going to need.
Joe, Glenn talks about some of those steps towards, again, this path to 5G, if you want to call it that. When he says steps, those are analogous, I would imagine, to challenges. What are some of the challenges in millimeter wave technology?
It can be broken into a few buckets. The first is understanding the first principles. And the first principles that, as we see them, are one, who's already invested heavily into bringing 5G together? And that group includes a lot of federal governments globally who have invested heavily in chipsets, CMOS, GaAs, gallium, silicon, germanium, other chipsets. And they want their premier technology companies to then succeed in building into 5G systems. So what are their priorities? Two, globally harmonizing a lot of the bands. Understanding that some companies are going to come out with amazing technologies and they're going to get stopped at the threshold, right at the door, because they're not going to be allowed to use those bands in many respects because they're not harmonized. There's going to be a mix of unlicensed, lightly licensed, and licensed bands. Past is prologue. You never see the big carriers rolling in to any band in a meaningful way unless they can own some of it. And so the licensed wide area bands globally typically are in the 24, 26 gigahertz, 28, 31, and 38 to 40 gigahertz. For example, in the US, the largest contiguously licensed band is the 38 gigahertz band, from 38.6 to 40.0 gigahertz. That's 1.4 gigahertz of spectrum. Another part of the education, first principles. People tend in the wider scope of things to look at fixed wireless and wireless in general as kind of static, and it's not. For example, 400 megahertz of spectrum at 24 gigahertz at IEEE recently, it was discussed. NTT put 23.5 gigabits over that. So when we hear Samsung and others talking about gigabit to the handheld, that's not outrageous at all. When you start looking at the advancements in the heavier bazookas that'll be out there for fixed wireless.
A lot of talk about the V-band solution to realize 5G technologies one day, but also for the proliferation of 4G technologies. What role does V-band play right now in that realization?
Sure, yeah, and it was mentioned a couple times with the other panelists here. V-band is great for point-to-point wireless backhaul for small cells, because small cells are typically closer together than in the traditional 3G, 2G models where cell sites were a little bit further apart. Now they're a little bit closer together. 60 gigahertz provides a nice short reach, and you can reuse the spectrum better off because your propagation characteristics of 60 gigahertz are so short. The other thing with 60 gigahertz is it offers you higher channels, or larger channels, which equates to higher capacities. So then you can have the multiple gigabits on the wireless backhaul to accommodate the gigabits per handsets that they're talking about for the 4G, 5G type networks.
Farouk, any standards deployed or organized or implemented for, again, realization of a 5G network one day, maybe by 2020? And if there's not, will that inherently push back this proposed deployment of a 5G network?
Our goal is to have 5G standard ready by 2018 as part of 3GPP release 14, which will allow us to deploy 5G starting in 2020. So we see, in fact, our projections show the gap between available network capacity and the demand continue to increase in the next 5 to 6 years. And this continues increase in capacity demand, along with the fact that new emerging applications like Internet of Things and cloud computing require lower latencies, will accelerate the development schedule for 5G.
Glenn, do you think there's a standards development for the path to 5G is moving at a pace that's consistent with the technology that's also growing?
Yeah, it's always a good question. I think standards never move as quickly as we want them to, but I think in this case, as he pointed out, that there's definitely a motivation to do so, and I think we're seeing a lot of proof of concepts and experiments now to actually iron out the wrinkles in those approaches. I guess I would just add one more thing is, we talk about microwave spectrum or wireless spectrum. There's also the ability, and it's becoming more than just an idea, but Wi-Fi offload to augment the wireless spectrum as well as the fixed line spectrum is also very important. You know, there are a lot of vendors out there that are looking at their small cells with not just the wireless uplink for traditional microwave or nanometer wave, but also for carrier grade Wi-Fi. So I think that's another way to augment the bandwidth capabilities that we're going to need. And of course, Wi-Fi is going through its evolution too. You know, it's going to be the next gen Wi-Fi that's going to also help. And I think the other side of the coin is this: we've talked about backhaul, which is obviously a real focal point, but there's also an issue with front haul between the antennas and between the antennas and handsets. And with 3G and 4G, there was one protocol, one technology to do that. I think with 5G, we may see additional alternative technologies there, where you could start to use some of this new spectrum, some of these new wireless techniques to actually deal between the base station and the handsets. And that's a ways off. I think that's going to be closer to the 2020 range. But it's also just another arrow in the quiver, if you will, to solve the bandwidth problem.
And just to add to that, another key driver for 5G is to reduce the cost per gigabyte of data transmitted. And this is possible in one way, as many of us here are promoting, by using higher millimeter wave frequencies, where spectrum use is lighter and a lot more of it is available. When we can bring down the cost of acquiring a spectrum, as well as greater capacities provided by beamforming and also energy efficiencies, the cost per gigabyte of data will come down, which will provide incentives for deployment of 5G systems.
Joe, I know you just came back, well, not just came back, you came back earlier this year from the National Spectrum's Managers Association. They talked about non-line of sight technologies. Where are we right now on NLOS?
There's been some exciting developments. One is there's a proven ability now, and there's a lot of white papers out there from a variety of manufacturers and other engineers that are showing that you can get not only through a tree line, but you can get around corners. And that's been established academically and in practicality. So that's a big development. When you combine the ability of using higher and higher capabilities of the chipsets, the exponential processing power, with the fact that with small cells that can be leveraged not only for backhaul but for front haul and for basic retail connectivity, you start putting together a lot of the strengths of these upper bands, these millimeter wave bands. It was a big deal back in 2000 when the ITU, the International Telecom Union, published a paper with all the global governments showing you get 200 links per square kilometer in these upper bands. And unlike, let's say, down at 900 megahertz where the traditional 4G networks operate, where that spectrum will go through walls, will go for many, many miles, and you can't reuse the spectrum. Here you can reuse spectrum again and again and again, and 200 links per square kilometer is almost nothing now compared to what we can do with small cells in the millimeter wave bands. So you're going to be talking thousands and thousands of entities being able to move around in a small area, and the teledensity is going to be much bigger, and the channel widths are massive. One 38 gigahertz channel is 100 megahertz. So that's a big deal.
And our channel measurements show that the propagation is different at millimeter waves compared to lower frequencies. At lower frequencies, it's more about diffraction, where waves can go around the corners. At high frequencies, it's more like light rays. It's more like reflection. So you can still do non-line of sight, but now it's going to be based on more reflective transmissions rather than diffraction. So, but we can take care of that by smarter hooks in the system design to leverage the reflections and still providing the non-line of sight coverage.
And DragonWave's recently done that testing in Ottawa, where we've proven out near line of sight, on line of sight SIPs running at very high frequencies in a small cell type environment.
You're saying non-line of sight or line of sight?
Non-line of sight.
Now, you also work and do research on line of sight technologies, particularly supported by the 70 gigahertz E-spectrum band. Where are you right now on that, and how will that, I guess, again, realize this path towards 5G?
Sure. So we're in the final lap, as I'd call it, for our E-band product. We feel E-band has a strong play in 4G, 5G networks. There is a lot of spectrum available in E-band, but it's also very important to be spectrally efficient in the band. Because as more and more users and more operators are trying to look at E-band, you need to be spectrally efficient up front. And by spectrally efficient, meaning high order modulations, narrower channel sizes, pushing more bits per hertz over the radio. And this is allowing us to look at 10 gig systems over our E-band product.
Farouk, I want to ask you what your perspective is on DragonWave's and Fiber Towers' efforts for build out for 4G and then one day 5G. From where you're sitting, how do you see that playing out?
We believe that industry will move from proprietary backhaul technologies to standard-based solutions. As part of Samsung's 5G design, we consider backhaul or the front haul, as pointed out, as an integral part of the overall system design, where the backhaul links and the base station to mobile station links can share the same spectrum due to directional nature of the millimeter wave transmissions. So this means that the backhaul and mobile links need to be co-designed for optimal overall mobile network performance. So this means this will have an important change in the overall network architecture for the 5G system.
How much of that is going to be site dependent? I would imagine we need a lot of planning and simulation tools to look at the topology and the specific environment that it's going into in order to pick the right frequencies and the right technologies.
Yeah, sure.
So I think there's probably a lot of effort going into modeling and determining these propagation delays and everything.
Exactly. And with the adaptive beamforming technologies using a large number of antennas, we can form narrow beams 10 degree or less wide. And by changing the phase on each antenna, we can rapidly switch the direction of the beam just like an hyperactive searchlight. So this means that coming back to your question, once we have this capability, it doesn't matter if my link is base station to base station links or base station to an hub link or the base station to mobile station links, because these beams can be switched by changing the phase to set up the link on any of these access points.
Glenn, we talked about the use of spectrum bands for millimeter wave technologies, for new technologies. I want to ask you about what spectrum bands, if you could just recap for us, what spectrum bands are ideal to support small cell technologies?
Well, I think the V-band, the 60 gigahertz is well suited because of the short attenuation, so that it can be reused in a metro area, where the traditional bands typically have to be point-to-point or and they're very heavily licensed. So I think the 60 gigahertz or V-band has a lot of potential there. Also, there's situations where I know operators are a little concerned because it's unlicensed, the sub 6 gigahertz range. There's been some work done on that. So, but then you get into the interference with Wi-Fi and some of the other devices using those lower frequencies. But I think when we talk to operators and when we hear back from them on what do they want, right now the environment's like, I want everything. I want a toolkit that will give me one of these and one of these and one of these. But then when you press them on it, they will standardize on a set of technologies. They're not going to use everything under the sun to make it happen. So I think that's still in progress now. Small cells, the outdoor versions are just beginning to be deployed. So I think we're going to start to see some best practices and some proof points come out pretty quickly. And a lot of the options will be pretty well known.
Joe, would you agree that the V-band is ideal for cost, coverage, and building it penetration?
It's definitely part of the solution. I think there's additional bands. Each band has its own little charms. And there's point-to-point license bands, which were used heavily. That's when MCI came out of Microwave Communications Inc. for long haul, huge dishes, 6-8 feet tall. Then a lot of networks that are backhauled, including the biggest operators in this country, have thousands and thousands of links that are usually anywhere from 2 to 5-foot antennas mostly. There's some bigger foot antennas as well. And now we're getting into the miniaturization and the small lower profile systems, and they'll be anywhere from 24 gigahertz wide area licensed, 28 to 31 gigahertz wide area licensed, and 38 gigahertz wide area licensed. Those, and then up to 60, and then 70 to 90, and eventually above. The value of the wide area licenses to the folks who are putting in the heavy capital, the people who are saying, AT&T is quite clear, they usually put in $60-some billion over certain periods of time when they build. They're not going to do that just on unlicensed, but they value unlicensed like they do today. That's why you have Wi-Fi in your phone, and it's great. But at the end of the day, they're not going to put all their eggs in that basket. It's just not going to happen. They're going to go after these license bands as a pivot point, and until they know they're harmonized and available, not only here in the U.S. but everywhere else. Because the equipment manufacturers are going to bring down price and cost points once you get more of that dynamic going. Then we're going to see the things really opening up and moving. And there are issues here domestically in the U.S. The FCC's policy for renewing licenses in the wide area license bands in 24 through 40 gigahertz has been criticized, and we're one of the critics in some respects. It was pursuing, you have to build a certain amount of links per square mile or per certain amount of links per million people in an area. And a lot of folks, including Fiber Tower, were saying, well, what if the customer isn't ready? You just don't build backhaul links or any links to nothing. How about taking R&D and using that as a measure? Are you engaged in R&D and bringing real solutions to the market? So those kinds of regulatory fixes are really needed before private capitals can be comfortable to jump in a real way. And once private capital's comfortable, and once the big carriers who are really going to be buying the big infrastructure here are comfortable, and we have the global harmonization, when those first principles come together, then this thing's really going to roll. And there were some interesting discussions earlier today in one of the other panels about, for example, in Korea, the Olympics in 2018. Won't that be a great platform to take 5G and show it off? So, there's going to be pressures to bring this, before 2020.
You're all looking to operate in the millimeter wave and microwave spectrum. How do you, and I'll start with you, Eric, how do you see the spectrum landscape and utilization of spectrum playing out, let's say, over the next 5 years?
Yeah, so I think a lot of the deployments in microwave backhaul in the last decade has been focused around the 6 to 23 gigahertz. The next 5 years, I think that's going to start to move into the in the area licenses potentially 60 gigahertz and 80 gigahertz. There's only a finite amount of spectrum in the lower bands. That being said, it's also we're starting to see advancements in modulation techniques such that you can take advantage of the existing spectrum out there and push more bits per hertz in the lower spectrum. But I think you'll see a combination of the two, of moving to the higher bands as well as pushing more bits per hertz in the lower bands.
Farouk?
At millimeter waves, using beamform technology, I think we can also foresee some new innovative spectrum sharing approaches. As we can switch the beam when there is interference. This means hypothetically in a given geographic area, multiple parties can share the same spectrum, and the interference can be avoided by using adaptive beamforming technology.
Glenn, the spectrum landscape over the next 5 years?
Interesting. I think I kind of agree with everything that's been said here. There's going to be a plethora of new spectrum coming on board. There's also going to be massive reuse and continued use of what's already licensed and approved. I think the regulatory agencies are going to have a big impact on how fast these newer technologies can get adopted. And then I guess the other side of it is the operators can be looking for this not to be a separate technology, but to be part of this end-to-end solution. So I think the other challenge we have is, yes, you can transmit a lot of bits over this new technology, but it has to be managed and provisioned and controlled. And I think that's going to be the other challenge. Is, 10 years ago, the microwave sat there and it was point to point, and as long as it was healthy, everyone was happy. But now I think we're looking at traffic management, dynamic bandwidth allocations, a lot of the stuff beyond just the link. So I think that's going to be another aspect where SDN, NFV type technologies are going to come into play.
I think it's always interesting to be progressive and forward-thinking, and gives us a lot to talk about between now and 2020, maybe when 5G network is really realized and deployed. Keeps me employed as well. Something to talk about. Joe, it was nice meeting you. We haven't met before, but thanks for being here.
Thank you.
Glenn, as always, thanks for being on our program. Farouk, we met earlier today. Well, we met before, actually.
Yes,
we
yeah.
talked before. We met at the gym this morning.
Yeah.
And it's nice to have you on the program. And Eric, thanks for filling in. I know that was a last minute change.
no problem.
there. We appreciate it. Thanks so much, and we'll see you next time.
Okay, thank you.
All right.